Okay, I'll try and make this as quick as I can. The answer to this is the buffer region resists changes to pH, which is what your textbook says. But it doesn't make a lot of sense. They really should add that are not aligned to the pKa of the acid, or if we're talking about weak bases, pKa of the base. But we'll just look at the one example here, acetic acid. So mathematically, doing the calculations, all 1 molar acids, strong acid over here. Where is it? Strong acid over here. Doing the drop, the 50 microliter drops, and then without the buffer effect, and then with the buffer effect, talk about this later, you get this here for the strong acid, this for a weak acid without a buffer effect, and this with a little dip for the weak acid with the buffer effect. So as you're adding sodium hydroxide along here, the buffer region is doing the opposite. It's not resisting changes to the pH, it's accelerating them, and the pH is radically changing. And so what you really should be saying, it might, even down here, what you really should be saying is it's resisting changes to the pH that's not equal to 4.74. So it's getting a stronger and stronger ability to resist changing away from 4.74 because the conjugate base is pushing the equilibrium to the left-hand side. Now, so that's the answer there. That's the red. That actually makes sense. Not buffer region resist changes to pH. Buffers do resist change to pH, but in a titration situation, it's only resisting changes to the pH that are not 4.74. Okay, so this little dip here, calculation-wise, and it's more extreme with the 2 molar, makes makes a lot of sense with the equations, but it didn't make a lot of sense conceptually. And so what I did was I just tried to do a better job experimentally. So I calibrated the pH meter, and it took a little while here to get down to it, but it kind of did get down to the 2.37, which is the value it should be. It's not really there. It's sort of hovering between 2.34 and 2.39. So it kind of hovers 0.05. And then, so there's a really good mixture in there. And then I use a microtiter pipette here, which is, just try and slow that down, set it exactly 50 microliters. So quite accurate. And then I put it in there and just wait. Just let that play. And it goes up, definitely does not go down. So the experimental evidence doesn't support the calculations. And then I just keep adding more and more to it just to prove the point that it does definitely go down, and it does curve, and it does it's getting closer and closer to 4.74, which is fine. And then to verify it, I went, because I already have the 2 molar calculations, I grabbed the 2 molar acetic acid. And this time I'm going to be really extreme, because this should be a 0.4 drop according to the calculations. Huge drop this time. And that's adding 50. So I'm going to add it in tens and tens and tens, so it's really clear that it goes down. And what you can see is from the get-go, it goes up. And if you do the calculations on that, those numbers are approximately correct. So after about 5, it should be 2 point, I forget the numbers now, but I did check them before and they're not too far off. All right. And so it definitely goes up and up and up when I've divided a drop up in between. Now I'm just adding whole drops. So the experimental evidence definitely does not support the calculations. So my students know I don't like Henderson-Hasselbalch because it's too physics, it's too derived without assumptions. I wouldn't mind banning the Henderson-Hasselbalch. And so what I did, so this is the assumptions here, the calculations with the assumptions. And ChatGPT is hopeless. It can do their calculations, but it just lies to you and doesn't give you any explanation at all. And so what I did is I went back and didn't allow the assumptions with the full Rice diagram calculations, not Henderson-Hasselbalch. It uses Henderson-Hasselbalch, by the way, unless you explicitly tell it not to. And it always does the assumptions. And it just tells you the dip is correct as well. And so here I'm not going to allow the assumptions. And I know my algebra is not good enough for that. So I just did it on an online algebra calculator. And yep, 2.5, it's not that far off. And it does go up straight away. So the issue is with the assumptions. So the assumptions will mean that sometimes your calculations are incorrect. So the dip is not real. It's only real because of the assumptions. Okay, so that's the long story. Hope that was helpful. Right, bye-bye.